The last thing we have to talk about here is what's called the change of base formula. This is the formula. This is the formula that allows you to calculate logarithms of other bases on your scientific calculator. So anyway, because most scientific calculators just have common log and natural log and nothing else. Some of the fancier ones, you can fill in a different base. But anyway, so here's the formula. If you want to take log base b of m and do it in terms of a different base, it works like this. So log base b of m is equal to log base a of m over log base a of b. Now, 99 times out of 100, that's going to look like this. Or this. Because those are the ones you can do on your calculator. Now I will say this. If you have one of those fancier calculators that can do just straight up like, I could type in log base 4 of like 50, I'm still going to want to see this kind of work on the test. I'm still going to want you to do it that way. Understood? So, let's try this out. I personally have no idea what power of 5 gives me 140. So I have to figure that out. And it doesn't matter if I use common log or natural, as long as you don't use one up top and a different one on bottom. So, what would this calculation look like? And then you need to calculate that. So I take the log of 140 and divide it by the log of 5. And I get roughly 3.07. Now, let's say I wanted to compute log base 7 of 2506. Just to prove a point, we can use ln here, it doesn't matter. So what would that look like? do that. Looks like that's about 4.02. Sound pretty good? All right. So that's the end of 4.3. So let's go on to 4.4. In this section, you're going to need to have an intimate knowledge of how exponentials and logarithmics work together. Now, there are going to be three methods for solving these equations that I'm going to show you. Method 1, get the same base. Because if I can write an exponential like that, if b to the nth equals b to the nth, what would that mean specifically? Say that again. Yes, they are the same. What specifically would be the same? I'm so sorry. Well, yeah, but if b is the same, and I say b to the nth equals b to the nth, specifically, the two exponents have to be the same. So what you can do at that point is, if you can set this up with the same base, you can just kill the base off and look at the exponents. So let's try it out. $16 is 2 to what power? No. It's 2 to the 4th. 2 to the 3rd is 8. So you got 2 times 2 is 4 times 2 is 8 times 2 is 16. So it's the 4th power. So what we can do is we can write this as 2 to the 3x minus 8 equals 2 to the 4th. So at that point, what could we do? I can't hear anything today. Okay, so how would that look? Yeah, 3x minus 8 equals 4, because since the 2's match, the exponents have to match. So literally you could just add 8. And solve. Say that again? Right. "27 is not a nice power of 9. However, 27 and 9 are both a power of some other number. 3. So 27 is 3 cubed. And 9 is 3 squared. When you raise a power to a power like that, what happens to the powers? No, you multiply. So basically, I'm going to need to distribute this 3 to x plus 3, and this 2 to x minus 1. So that's going to look like 3 to the 3x plus 9 equals 3 to the 2x minus 2. And now, it should be fairly obvious where you proceed from here. You do the same thing we did on the left. Now, as you might guess, a lot of times you can't do this. Because a lot of times you'll end up with like 2 to the 3x minus 8 equals like 17. 17 is not a power of 2, and you can't easily force it to be either. So there's got to be another way to do this where if the bases can't match, you can still solve. That's what we're going to do after I render this video.